So today we're going to talk about Diffie-Hellman, Diffie-Hellman key exchange, elliptic curve cryptography, and I hope that you'll have a very good feel for these ideas and possibly be able to implement them yourself. But remember, never create your own cryptography. There are a lot of cryptographic libraries and there are a lot of little coding bugs that could lead to developing something insecure. But having a good understanding of how these algorithms work will help you to write more secure programs that use these algorithms and use these secure libraries. As always, this blackboard section of the lecture is going to focus on general ideas, and the PDF covers all of the specifics. I hope you have a great time listening to this lecture. Welcome to lecture 13. So last time we talked about TLS, and this time we'll talk about the algorithm that makes that protocol possible. In particular, we'll talk about Diffie-Hellman key exchange, and then we'll extend that to the idea of elliptic curve Diffie-Hellman key exchange. And let's just remind ourselves of the issue. So what we want to do is we have two parties communicating, Alice and Bob, and Alice and Bob want to exchange public information. And using this public information, they want to derive or calculate the same symmetric key. And anyone with access to this public information, like Daniel, should not be able to calculate this key. So this should be impossible. And so how could we do this? So let's talk a little bit about a general idea of Diffie-Hellman key exchange, and then we'll look at some details. So a common way to present this is by using the analogy of paint, and it helps build up an okay mental model for thinking about this. So Alice and Bob both agree on a common paint color. So Alice is going to say, my common paint color is yellow, and Bob does the same. So they say, okay, we'll agree on this common paint color of yellow. And then Bob will pick a color that Alice doesn't know anything about. And so he'll mix this secret color. Let's say he picks blue that Alice doesn't know about. And when he mixes those two, he's going to get some new color that is like lighter blue. So here's the resulting mixed color. And Alice is going to pick a secret color as well. And say Alice might pick red. And then she'll get an orangey color as a result. So her resulting color is this orangey color. That's what she gets in result. These colors are never shared. They're secret. Alice will send this color over the public network. So the attacker, Daniel, sees this color, and Bob will also send his secret color over the network. So Daniel sees those two colors. And then what Alice will do is she'll combine Bob's public color, which is this beautiful blue. See if I can select the right one again. This beautiful blue here with her secret color, which is this red. Right, so she's going to add her red to this blue, and then she'll get a color like brown. And so we'll pick a nice brown here, and we'll do it with her pastel sweeper. So she'll get a brown. And we'll do the same thing. He'll take Alice's color of yellow, and he'll combine it with his blue secret color, right? So plus his blue secret color, and he's going to get the same brown color out. And so that's the kind of mental model here, where you could have two people sharing information. So Alice and Bob agree on a common color. Then they pick a secret color. They both pick independently. The other person doesn't know about it. They combine their common color and their secret color to get their new public color. And then they share their public color with each other. In this case, Bob shares his blue, Alice shares her light yellow. And then they combine their information, even though I didn't pick the same colors here. These two colors are actually the same. Sorry about that. Then they combine their public information and their private information to get the same secret information on either side. And so that's the idea of the Diffie-Hellman key exchange. Okay, so let's talk about the math of it. So there are really 6 key steps here. So here we'll denote our steps here on the side, and then we'll have Alice and Bob. And so step 1 is to pick a shared parameter. We call this shared parameter G. So G is a number, and it's agreed upon. So it's a shared parameter agreed upon between Bob and Alice. And it's a fixed number. So you'll see when you generate these keys, they'll normally have a common value for G that's defined, and the generator that's normally picked is 2. Now we'll discuss why it's called a generator later, or if you're curious, you can go ahead and read the PDF. So in the second step, what Alice is going to do is she's going to generate a secret number. And so we'll just say A is Alice's secret number. And the way she's going to generate this is from some random source. So it's just truly randomly secret. And Bob will do the same thing. He'll also generate a secret number B that is random. And these are large random numbers, so very hard to guess. And then they'll calculate their public key. How will Alice calculate her public key? She'll take the shared information and combine it with her private information in some way. And the operation that we use here is exponentiation. So here's our public key, A, and we're going to take the generator G and raise it to A. And then Bob will do the same thing. He'll calculate his public key B by taking the generator G and raising it to a power B. So now you see, oh, it's great to pick 2, right? Because I can do this operation with a shift. So now that we have our public and private key, our private and public keys, now we have our third step where we're going to share it. So we're going to send, Alice is going to send her public key to Bob. And to prevent replay attacks where somebody could say, oh, here's the public key from last time, we're going to make this message unique. So we'll say, we'll have a nonce from A. So this is Alice's nonce. And Bob will do the same thing as well. So Bob will send his public key B and a nonce that he generates. So now this is the beautiful part, right? So now we have public information and private information. What we want to do now is we want to combine it to get the same shared key. Remember, that's our goal. Our goal is to get this shared key here. So let's see how we could combine the information to now derive some shared key. So this is our fourth step. So what does Alice have? Alice has Bob's public Bob's public key and her private key and Bob's nonce. So we could calculate the shared key. The way the shared key is calculated is we take Bob's public key and raise it to Alice's private key. And so if we think about what Bob's public key was, it's G to the B. So if we go ahead and we substitute that, we'll get our generator G to Bob's private key times Alice's private key. We've just substituted here. And so if Bob does the same thing, if he takes Alice's public key, A, and raises it to his private key, B, then if we look at what Alice's public key here is, G, this is equivalent to doing G sub A, that's what A is, to B. And this is the same thing as G of BA. And so now we have two keys here that are the same value. So these two values, S, or secret keys, are the same. Great. And you might say, oh, that's great. I see how we get our secret keys. But these secret keys aren't our final key. Right? So we need to use a key derivation function to transform them into the form that we can send to a block cipher, right? These are going to be numbers. Oh, we want our key to be some uniform random string. And so in the fifth step, we're going to run our secret key through a key derivation function. We looked at a very bad key derivation function before using the linear congruent random number generator. And then we said that there were other better key derivation functions. The one that's commonly used here is HKDF for the HK key derivation function. So you'll pass S that key derivation function, the nonce of A, and the nonce of B. And that will get you your key that you can use in your block cipher. Bob does the same thing. He calculates his key by doing the HKDF of the same symmetric key, and he also has the nonce of A and the nonce B. So every time we establish a connection, we have new nonces for A and B, and then that means we have new keys as well. Even if we don't change our secret keys, right? And so this means that we have this notion of forward secrecy. Even if somebody steals our key, right, from a previous session, it's not going to let them decrypt the keys for future sessions. If somebody was able to steal this key K, right, from this session, because the next session we're going to calculate a new K. So they will be able to decrypt the data from that session. But in the sixth and final step, we'll go ahead and we'll just encrypt our data with our key K. And we can do that on both sides because both people have arrived at the same K. So as always, we have this issue of saying, oh, we want to go ahead and calculate. We want to go from the public key, right, to the private key. As an attacker, you're thinking, oh, how could I do that? So the reason that we call the generator G is because it's a series of multiplications, right? So if A is 3, then this is equivalent to saying G times G times G. And so because we're multiplying a number by itself, that's where the term generator comes from. It's a math term. So how could we crack this, right? So you might say, okay, I have to crack if my public key A is calculated by taking G to my private key, then why can't I calculate A, right? Doesn't this mean that I could calculate A by simply taking the log based G of little a? So I'm just going to go ahead and calculate log base G of little a, and that should give me big A back, right? And this process of exponentiation is really fast, right? We can do this with shifts really quickly. But to go in the other direction, to actually calculate the log of A is really slow. And to give you some perspective on how large these numbers are, this could be 248 bits long. And in cases of really secure keys, they could be 3072 bits long. And so it takes a lot of computation power to actually go ahead and calculate the log base G of this value A. And in particular, this is going to be a discrete log. And so doing that's actually very difficult. We don't know how to do that super efficiently for large numbers. And that's where the security of this comes from. People have proposed quantum algorithms that will be able to take care of small keys. And there's some heuristics that can do smaller keys. The key idea is that you want to pick a large key. And in this case, the recommended key size is 3072. And so the security of this whole scheme centers on this idea that calculating this is a little difficult. One of the things that I've not included in this description here is that all the operations on that table are mod p. And that's what really complicates this process of calculating the log. Now that we've discussed Diffie-Hellman key exchange and we've seen how public information can be shared to derive the same secret key, let's talk about an extension to this with this notion of elliptic curves. So because we think that the discrete log problem could be solved in the future efficiently when we have quantum computers, we want to think of other mathematical problems that are really easy to do in one direction, but very hard to reverse. And so instead of computing on numbers, we're going to compute on points. And so here in particular, we're going to work with geometric representation of these points, and we're going to work with this idea of an elliptic curve. An elliptic curve is defined by this following equation: y squared equals x cubed plus ax plus b, where a and b are constants that define the curve structure. So depending on the values of a and b that you pick, you get a different curve. But all curves have this general form. They look generally like this, where we'll have some loop like that. So instead of the values being integer values, remember from before our generator was 2, right? That's just an integer value. A, B, big A, little a, they're all integer values. Here we're going to be working with points. So our generator is going to be some point G that has an X and Y value on the curve. And we're going to have some public key, P, that is just some other point on the curve. And so it's another XY point. And the way we're going to calculate our public key is it's going to be equal to our generator, XY, point on the plane, times some scalar number, N. And so here, in this case, N is going to be our private key. How many times do we multiply G? So you just noted this by private key here. So how many times do we multiply our generator G by N to get to the point P on the curve? So the common curve that's used in Bitcoin and some other applications is the SEP 256 K1 curve. And it just has the form y squared is x cubed plus 7. So in this case, a is 0 and b is 7. NIST recommends using the P-256 curve or the curve 25519. Those are the ones that NIST recommends. And you can look up the equations for those curves on NIST. So we'll focus on the SEP key today because it's commonly used in Bitcoin. And it's the one I'm most familiar with. What does it mean to multiply a point by a scalar? We haven't seen that before. And what does that mean, particularly in the context of elliptic curves? Is there some unique property of elliptic curves that makes this interesting? Yes. It turns out multiplying a point by a scalar is really easy in elliptic curves, but doing something like dividing 2 points is really hard. And so let's talk about this idea of multiplying points. So on our elliptic curve, I'll just draw it like this. Let's say we had 2 times g. This is equal to g with point g, x, y, or generator. That's simply going to be equal to our generator xy plus our generator xy. So if we can do point addition on the elliptic curve, then we can do multiplication. And so here's our elliptic curve. So we have our generator g here on the curve. And the way we do point addition in elliptic curves is you'll draw a point tangential to g. So this is our point g. And then wherever it intersects the curve, you reflect it over the x-axis. Reflect the x-axis. And wherever it intersects, that is going to be g plus g or 2g. And so remember, we're not multiplying integers here. So I should say gxy, 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 right? We're multiplying points or adding points. Or adding points in this new domain of elliptic curves. And so this is the property of how you add points in the elliptic curve world. And so 4 is going to just be gx plus gx. 4, may I do it like this? Gx times 4. It's going to be just gxy plus gxy. And so you would repeat that procedure again. You would take the tangent here, say it would intersect here, then you would reflect it. And this would be your 3 gx. And then you would continue that process again, one more time to get 4 gx. And so that's the basic idea. So that's the simple idea of how we're going to do multiplications of points in this elliptic curve world. And so now let's look at the elliptic curve Diffie-Hellman algorithm. Check that down. So there's 6 steps like before. And in the first step, we're going to pick our shared point. So we'll have Alice and Bob here. And just denote that. We're going to pick our shared point, gxy. And then we're going to generate some random integer value. This is going to be our n. So in step 2, generate some random value. And same thing for b. Right. And then we're going to calculate our new public key by taking our generator point, xy, and then performing that scalar operation that we did before. So we're just going to take gxy and we're going to multiply it by a. And it's really easy. There's a lot of really quick algorithms for doing this in the elliptic curve space. And so then we'll get our public key AX, which is a public point on the curve. So this is going to be an XY value on the curve. And B will do the same thing. We'll calculate his public key pair. In this case, it's a public point by doing scalar multiple of GXY. And then they'll go ahead and they'll share their keys. So that's important. So then B is going to share, or Bob is going to share his public key or public point, BXY, and a nonce to prevent replay attacks. And Alice is going to do the same. So she's going to share her public key or public point, AXY, and a nonce. And now, this is where the amazing magic of elliptic curves comes into play, right? We're going to go ahead and calculate that shared key or shared point on our space. And from that shared point, we're going to go ahead and derive our final key. So how do we calculate our shared point? Alice is going to calculate that shared point. So we'll call that shared point KXY. So she's going to take Bob's secret key, BXY, and multiply it by her private key, A. And so what's BXY? BXY is just B times GXY. And then we multiply that by A. And so then this is just A times B times GXY. And Bob is going to do the same. So he has his key. He wants to calculate KXY. And so he's going to take Alice's public point, AXY, and multiply it by his private scalar. That's going to move it around the curve. And then AXY, right, is just GXY times A. And so the final result here is just going to be GXY times A times B. And if we just write it in the other form, that's A times B times GXY. So both keys are the same points in space. And then these are points, right? So we want to transform them into a uniform string that we can pass to our block cipher. And so how do we do that? We just run them through a key derivation function. And because we have 2 points, we have X and Y, right? There are 2 values here. It's common to just take the X value of the point and pass that to the key derivation function. So we'll have our final key K, and we'll use HKDF, that key derivation function, and we'll pass the X value of the point KXY, so just denoted by KX here, because we're just taking the X value, and the nonces, right? So A and B's nonces, and this gives us forward secrecy. So K is just going to be HKDF and K of X here, which is the same to calculate the final key to go ahead and do the block encryption. And so from this point on, in the final step, the 6th step, all the content is encrypted. So that's the basic idea. And instead of doing it with exponentiation, we're swapping out the exponentiation operation for an operation on elliptic curves. As always, we want to say, we know how the public key is calculated. So can we look at the public key and derive from that the secret key? So let's particularly focus here on A's value, because that's what we did last time. So A's public point, AXY, is calculated by taking the generator, GXY, generator point, and performing that multiplication operation. And so ideally what we're looking for, because the generator is public, we're searching for this secret value A. And so A should be equal to A sub X divided by G of XY. And remember, these aren't integer values. So this is not an integer division. It's division operated on that elliptic curve. And we don't have an efficient algorithm to compute this. And so that's what makes it secure, because we can't compute this division here in an efficient way on elliptic curves. So a division of 2 points on an elliptic curve is something that we don't have an easy, efficient algorithm to solve. And that's where our security lies. Big takeaway is that a lot of the security of these encryption algorithms is based on the fact that solving the discrete logarithm problem is hard, which we think could possibly be solved by quantum computers. And then the second one is solving this division problem on elliptic curves is hard. And so we don't have a solution for it. And so that's where the security comes from. So just like a big kind of takeaway is that you want to find an operation that's easy in one direction. So like exponentiation or this multiplication in elliptic curves, but intractable in the other direction. And that's the basis of what makes this encryption possible. So now we'll talk a little bit about writing a secure socket using TLS. And I've left that discussion for the PDF. Take a look, all the code is there, I've annotated it, and you can read through it slowly. Okay, that's it for today's lecture. I'll talk to you soon.
Great. So if you're enjoying these lectures, feel free to check out the full lecture series on Udemy. The link for that full lecture series is in the description below. Thanks.